Amanda pointed out something on the forum that you guys should help me with. So I think if you see the videos, if I write too high, it doesn't show up. The reason is that several people are using this room, and I'm by far the tallest one. Everybody's much shorter than me, and no one can reach up there. And so they just, and you can't fit the whole height of the board, so we had to choose another height, and I got outnumbered. So that means that this part doesn't show. So if I write in this part, then please let me know. I'll try to remember, but. Okay, so let's see. We were talking about elimination, right? And the ideas we said was given an ideal. Let's say in the polynomials over x1 up to xn, we wanted to compute the elimination ideal. Elimination ideals. And these are the following things. So it's the intersection between I and the ring of polynomials in the variables xi plus 1 up to xn. In other words, these are the polynomials in I that don't involve the variables x1 up to xi. Okay? I guess there's one thing that I didn't discuss last time, which is, and we should discuss it. So are these actually ideals? Because I shouldn't call them elimination ideals otherwise. So what do you think? Are they ideals? Think about that for a second. So in other words, if you have a polynomial in these variables and you multiply it by some other polynomial, is it true that it still only uses those variables? Too many of you are nodding. The answer is no, actually. But of course, I called it an ideal, so it should be confusing. But you see, if you take a polynomial that doesn't involve the first I variables, and you multiply it by some of the first I variables, then you're going to fall out of the ideal, right? So the reason these are called ideals is because they're ideals, but in this polynomial ring, not in the big one. So they are ideals in here. Yeah. So that's something that we should be careful about. But then whatever reason you had in mind why you nodded, now it's actually right. So we wanted to compute these, and I told you that there's this amazing thing, which is that if you have a Gröbner basis for this ideal, which you can construct, so let G be a Gröbner basis for I, and with respect to the lexicographic order, that makes x1 bigger than x2, etc., bigger than xn. Okay. Then I say, consider this set Gi, and this is the set of polynomials in G that do not involve those variables that we don't want to involve. Okay. So the polynomials in G that only involve the variables xi plus 1 up to xn. And then I said that basically these guys generate this elimination ideal, and in fact there are Gröbner bases for it. So Gi is a Gröbner basis for this elimination ideal. Now whenever I say it's a Gröbner basis, but I have to specify with respect to what order, right? And if you think about it, that should be an order only in the last variables, because we're talking about the ring that only involves the last variables. And so this is the lexicographic order with the order of the variables being the same order, except that you forget about the first I variables because they don't appear. So I think I stated this theorem last time, but I didn't prove it. So I wanted to prove it now. Okay. But before I prove it, do you guys have any questions about what this statement is saying? Incredibly simple. If you want to generate the ith ideal, just look at the polynomials in G and see which ones don't involve the first I variables. And those guys are a Gröbner basis for the ideal that you want. So once you have this set G, this is immediate. Okay? Maybe before I prove this, I should give you an easy corollary, but a useful corollary. Because I told you that elimination works sometimes and it doesn't work sometimes. Okay? And remember what we said is basically that we wanted to, the way we used elimination was to use the last elimination ideal to see if we could find an equation involving only one variable and solve that equation. And then we look for the equations in two variables and solve those equations and etc. But if this elimination method is going to work, then you need that at each stage the elimination ideal should be non-empty. For example, if you think about the system of equations where I had an ellipse and a circle, I showed you an equation that involved y only, and we solved that equation. But it might be that there just isn't such an equation in your ideal, and if there isn't an equation involving only y, then you can't solve for y like that. Okay? But the nice thing about this is that this tells you easily whether this algorithm has a chance of working, because the elimination ideals are going to be non-empty if and only if they have a generator. We have generators for them, and so if there's at least one polynomial in GI, then this guy is going to be non-empty. But if there aren't any polynomials in GI, then there's not going to be any polynomials in II, which means that elimination won't work. So this we need this if we actually want to eliminate. And so this makes it very easy to know ahead of time if elimination has a chance of working or not. Okay, so here's a proof of this fact. So what do I need to show? I need to show that the initial ideal of I sub I is generated by the initial polynomials of, let me write it this way. The initial polynomials the initial monomials of the polynomials in GI. Right? This is what I need. And by definition, it's clear that this is contained in this, right? Because if you take any polynomial G in GI, then by definition, if you're in GI, then you're in II. Okay? And that means that the initial term of G is in this initial ideal. So, in other words, this is clear. There's really nothing to say there, except just remembering what the definitions are. And so this is the interesting part. So we need to take something in here and show that it's generated by these guys. Okay? And so what I'm going to do is I'm going to say I'm going to take some random polynomial in I sub I so that its initial monomial is in the initial ideal of I sub I. And I need to show that this initial polynomial is generated by these guys. Right? So I say this. I say that I know that G is a Gröbner basis for my whole ideal, right? And that means that the initial monomial of any polynomial in I, in particular f, is generated by the initial polynomials of the Gröbner basis. Okay? So that means that I can write some equation like this. where these are my generators, and the AIs are anything in my polynomial ring. Okay. So this just comes from the fact that the G1 up to Gm is a Gröbner basis and the original ideal I. Okay. And now I'm going to say the following. You see, the thing is that the left-hand side only involves the last variables. It doesn't involve variables 1 up to I. Okay? And so what I'm going to imagine is the following. Look at this right-hand side. Okay? So each one of these terms might or might not involve the first variables. And so what I'm going to do is that simply, I'm going to take everything that I see here, and I'm going to delete everything that involves the first I variables. Okay. So delete. Let me delete everything here involving variables x1 up to xi. So what do I mean by this? For example, it might be that A1 looks like this. I can't go very high here. Let's say that A1 looks like, I don't know, x1 squared plus x3, x4. Okay? That might be what A1 is. And it might be that the initial term of G1 is x2, x3. Okay? And let's say that I is equal to 1. Okay? So the first elimination ideal, I sub 1, consists of the things that don't involve the first variable, x1. Right? And so I'm going to say, well, I had this expression over here, and I'm just going to get rid of this occurrence of x1. So any monomial that appears when I do this, I'm just going to delete it, and I'm going to keep the rest of the stuff. So when I do it for this guy, I would forget about the x1 squared, and I would just keep the other stuff. Okay. So I do that for this term. Then for this term, for example, it might be that this term looks like this: x2 squared plus x3. And then maybe the initial term of Gm is x1 squared. So when I do this, well, I have two monomials here, x squared, x1, x2 squared, x1 squared, and x3, x1 squared. But they both involve the variable x1, and so I just forget about that altogether, and nothing survives here. Okay, so that's what I plan to do. Yeah?
F is a polynomial in your I.
Mm-hmm.
But when you say in F, that's just the first monomial?
Right, so in F is the first monomial appearing in the polynomial F.
So why is it equal to sum of monomials?
Well, I mean, the point is that there's surely cancellation here. Right? I mean, I know that this equation is true because in of Gm1 up to in of Gm generate the initial ideal. And so anything in the initial ideal has to be a combination of them. But you can be sure there's a lot of cancellation going on if you have this big expression and you end up with just a monomial. Okay? So I could build, yeah, I don't know. For example, if it looked like this. Let me change the example a little bit. So then you can see, for example, that this x1 squared, x2, x3 cancels this x1 squared, x2, x3. So this might be what goes on. Okay? But my point is this, that if I take the right-hand side and I just delete everything that involves the first I variables, then this equation is still going to be true. And the reason is that the left-hand side doesn't involve any of those variables. So what I'm going to do is that I'm going to take each one of these terms and whatever survives this process of getting rid of the first I variables I'm going to call alpha, I don't know, let's call it alpha 1, initial term of G1. Okay. One way of thinking about this is that you can think that the polynomial alpha k is what you obtain from ak by plugging in 0 into the first I coordinates and then leaving the other ones alone. So if you plug in 0 into the first I coordinates, that means that anything involving x1 squared is going to go to 0, and this one is going to go to 0, etc. Okay. So that means two things, that each one of these AIs becomes now an alpha I that is somehow a subpolynomial, so to say, of AI, but also some of these initial terms of GI are going to disappear. Right? For example, this guy disappeared in this case. And so I'm just going to keep track of the ones that survive, and I'm going to call them alpha. Let's say that the terms that survive are alpha A times the initial term of GA plus etc. plus alpha B initial term of GB. Okay? And like I said, this equation is still true. Okay? Maybe that's the easiest way to see that this is true is take this equation, plug in 0 for the first I coordinates, and the thing is that the left-hand side doesn't have any of those first I coordinates, so the left-hand side didn't notice that you plugged in anything. And the right-hand side gets changed. And so this is what happens when you change it. Okay. So what's the point? Well, the point is that in the way that I wrote this, now the alphas are a little bit different because now it used to be that the AIs were polynomials in x1 up to xn, but now I can say something stronger. I can say that they're polynomials only involving the last variables, because I threw out the first variables. Okay? And the other thing I can say is that the initial terms of these guys that appear also must involve only the last variables, because if they had any of the early variables, then I threw them out. Okay? Is that okay so far? Okay, so here's the beautiful thing now, that I claim that if the initial polynomial of gk involves only the last variables, then actually you know that gk itself, which is bigger, right? I mean, this is just the first term. But I'm saying if the first term doesn't involve the first variables, then you're not going to see those variables anywhere. Yeah? Do you guys see why that is? The point is that this is lexicographic, right? And so if gk involved any of the first I variables, then because this is the lexicographic ordering, you should see that in the initial term. If the initial term doesn't have them, then they're not anywhere in the polynomial. And so what that means is that actually I just wrote the initial term of f as a combination of initial terms of GIs that, you know, the GKs only involve the last I variables, but by definition they are in G, right? Because they're elements of my Gröbner basis. And by definition, this is exactly the set GI. Okay? And so what I just did is that I expressed the initial polynomial of f as a combination of things in this guy. I meant to only box it until here. This guy, etc. All of these guys, they live in the initial these are initial. These live in the initial terms of G such that G is in GI. Okay. And so what I just proved is that the initial term of f is generated by these guys. Okay. And this is exactly what I was looking to prove. So that's how it goes. Okay. End of proof. So I'll let you stare at that for a second and let me know if you have any questions about it. Yeah.
So we do have then that those GIs also generate the ith ideal, right? Not just the initial.
Right. So here there's something implicit that I didn't say, which is that I discussed that if the initial terms of GI generate the initial ideal, then the terms GI generate the whole ideal. And I said this in the context of Gröbner basis, where we said, first I said a Gröbner basis was something that generates the ideal, and the initial terms generate the initial ideal. But then I told you that to check a Gröbner basis, you just have to check the second property. If the initial terms generate the initial ideal, then you know for free that the polynomials generate the whole ideal. So in particular here, I sub I is generated by G sub I. That's right. Okay, any other questions about this? Okay. So really, this means that there are fairly complex systems of equations that you can solve. I told you that it's too ambitious to hope to solve any system of equations, but this somehow reduces the problem of solving systems of equations to the problem of solving single equations. And so if you know how to do that, then you have a good chance of solving actual systems of polynomial equations. And there's a huge theory of this. So if you are interested in solving systems of polynomial equations, this is another very good subject for the project. How to actually put these things in practice. Okay. Okay, so we're still talking about applications of Gröbner basis, and now I'm going to show you another one. This is it. So it's about computing with ideals. So like I told you, Gröbner bases are excellent for computing things. And so let me remind you that, let's say that you have two ideals, and let's say that you have generators for them. So maybe the first ideal looks like this, and the second ideal looks like this. Okay, so you have generators for them. Now you might remember from your ring theory class that given two ideals, there are several ways of constructing new ideals out of them. So for example, so here's some ideal operations. So for example, you can add two ideals and show that that's an ideal. So what this is things of the form I plus j, where I is in I and j is in j. Okay. So you can check that this is an ideal also. This isn't true generally for this is true generally for any ring, not just for polynomial rings. You might need to be commutative. I should think about it a little bit carefully, but for nice rings, this is fine. You can take the product ideal, and what this is that it's kind of similar. So you take the products of something in I and something in j. But now that won't necessarily be an ideal. But if you take the things of this form, then that's an ideal. Okay? So you can think of this as the set of linear combinations a sub k times a product of something in I and something in j, for k equals 1 to n, let's say, where the AKs are in your ring. Okay? So these guys are ideals in a ring. Okay? So that's another ideal operation, and well, by definition, it's clear that this is an ideal because I said it's the ideal generated by these guys, right? So there isn't a lot to prove there. What else can you do? You guys remember? You can intersect ideals and you're going to get an ideal. Actually, maybe that should have been the first one that I told you, because somehow we like to know if things are close under intersection and union. It turns out that if you intersect two ideals, you get an ideal. But if you take the union, you don't necessarily get an ideal. And it turns out that the smallest ideal containing the union is this guy. So you can kind of think of the sum as the union. Okay. But this is kind of generalities about ideals. Okay. Someone have a question? All right.
How is the product that much different than the intersection? Because if we take the product of things, take the product of I with everything in J, that's still going to be an I. If we take the product of J with everything in I, that's still going to be in J. So we have all the products are also going to be in both I and J, right?
But the thing is,
what are we missing, I guess, is my question.
so your question is why isn't ij equal to I, basically? I think that's what your question is.
No, why is it ij not equal to what I intersect J?
Do I intersect j? It's a good exercise, actually. So let's talk about it in the forum, but it isn't. But I see your point. I mean, the point is that the ideals are close under multiplying by something in the ring, and so you have to think a little bit about why these aren't the same thing. They are related. Could you put that in the forum, actually? I think I'll forget, but that'll be a good review question for ideals. Okay, so this is all nice, but there's a new feature in this class that we didn't have in the ring theory class, at least when I taught it, because back in my class we didn't talk about computing things, and very often people don't really talk about computing things and how you actually perform this, right? So for example, how do you compute the ideal I plus j? Do you really have to take every polynomial in I and I with every polynomial in j? Well, it turns out that you don't really have to do that. You can, I mean, generally we describe ideals by giving generators. And can you guys tell me a list of generators for this guy? It's just the union of the bases, right? Of the generators, right? So here the point is that, first of all, 0 is in J, right? And that means that the ideal I is in here. And so that means that all of these guys should be inside the ideal, and I can throw them in as generators. By the same reason, J should be in here, and so all of these guys I should throw in as generators. But the point is that with this and this, I can generate anything in I plus j. Because if I have an element of I plus j, let's call it little I plus little j, then you just use these guys to generate little I, use these guys to generate little j, and then add. So adding ideals is easy computationally. Okay. What about ij? Well, I guess I was a little bit loose in my notation here. So here I should have said that ik is in I and jk is in j. Okay, so the point is that we're looking at, here we have a generating set, right? The products of something in I times something in j. But that generating set is huge because it involves every element of I and every element of j. But as you can imagine, you don't really have to do all of this. It's enough to just do it for the generators, and you'll be in good shape. Okay? So if you just look at the products of something in I times something that one of the generators of I times one of the generators of j, that's going to be enough. So it takes a moment's thought to see why this is true, but it is true. So you just look at all the products like this. And that's the generating set for the product ideal, so that means that this is easy to compute also. Okay? What about the intersection? If you think about it, this is a lot harder, because somehow the starting point of these two guys is that you kind of start building from I and j into bigger things. Right? But here, you're kind of taking the common things that are in I and in j. And if you think about it, it's even hard to decide if this is empty or not. I mean, if I give you two ideals, how do you know if they have a common element? You'd have to find whether there exists a combination of these guys that equals a combination of these guys. That's not trivial. So it's hard to find a single element, let alone a generating set. Okay? And so this is a serious question. How do you generate the intersection ideal? But since you know that Gröbner basis can do anything, it seems, Gröbner basis can do this also. So I'll show you. So here's a proposition. This proposition has two parts. The first part is this. I'm going to consider the things. I'm going to consider this. Okay. What do I mean by this? I mean the things of the form t times I plus 1 minus t times j, where I is in I and j is in j. And what's t? T is some indeterminate. So where does this live? Well, I and j live in my ring with variables. So this is about polynomial rings, by the way. This was true in general, but we're going to talk about this for polynomial rings. So this guy involves polynomials, this guy involves polynomials, and so what we're going to do is that this is going to involve polynomials in the variables x1 up to xn and a new variable called t. Okay, so this is a subset of the polynomial ring in variables t, x1, x2 up to xn. And what I want to claim is that this is an ideal. It's an ideal here in this polynomial ring. Okay? So let me just write that out, actually. So this is an ideal of what did I say? Polynomials in t, x1 up to xn. Okay? So this is the first thing, and you might wonder what on earth I'm doing here, because you don't see any intersection here. But that's where part B comes in, because part B says that the intersection of I and j is equal to this thing that I just wrote. Okay? And like I said, this consists of polynomials in n plus 1 variables, t and the rest. So what I'm going to do is look at this ideal, and I'm going to consider the things in this ideal that don't involve t. And I claim that the polynomials here that don't involve the variable t are exactly the intersection of I and j. Okay. Is the statement clear? I'm saying build some ideal. It looks artificial, but it's an ideal in a bigger ring, right? I'm talking about the ring of invariables, but now I go up one variable. I allow myself to use t, and I consider this thing, and I say this is an ideal. Okay? And then I say if I look in that bigger ideal and look at the things that don't involve t, so they're in my smaller ideal, then what I'm going to get is exactly the intersection ideal. But you see, what I'm saying here then is that this guy, by definition, is exactly the elimination ideal. The first eliminate, first or last? The first. This is the first elimination ideal of this guy. The first elimination ideal of ti plus 1 minus tj. And the beauty of this is that now you know how to compute intersections. Why do you know? Because you want to compute this intersection. And what I'm saying is this. I'm saying, well, first of all, you know how to compute this ideal. Why? Because you know how to compute sums. And you know how to compute multiplying by a t and by 1 minus t. So you can compute this ideal. Then you can compute a Gröbner basis for this ideal and use that Gröbner basis to eliminate the first variable. And when you've done that, what you have is the intersection that you want. So, conclusion. So we can compute I intersect j using a Gröbner basis for this guy. Maybe one thing that we should say is how do you generate this guy ti? Well, that's very easy because this is just the polynomials in I multiplied by t. So the way to generate them is just tf1 up to tfa. And the same thing for 1 minus tj. So that means that if I want to generate ti plus 1 minus tj, then I just consider these guys and these guys. And so then what I should do is just start with this ideal and eliminate the variable t using Gröbner basis. It's all very, very simple and very explicit. Okay. Now the nicest thing about this, do you have a question?
Yeah, you have, let's say, F1 and F2 in the generating in the basis for the ideal, right? Then F1, F2 is also an ideal. But if you generate by TF1, TF2, you won't get TF1, F2, you won't get this first one.
Well, the thing to remember is that these are generators as an ideal. And what that means is that you can take TF1 and multiply it by anything. And so the way that you generate TF1 is 2 is by taking this guy and multiplying it by F2, which doesn't live here. Okay. So we're going to prove this. Okay, how do I prove part A? I already did, actually, because here's the proof, right? Here's my set. and it's the ideal generated by these guys. So the proof of part A is this one. I've expressed this thing as an ideal. So what I should show is part B. So for part B, I have two inclusions to show. Okay. So let's go with the easy inclusion first. Let's say that f is in I intersection J. And I have to prove that it's in the other side also. Well, what I can do is f lives in I and f lives in J. And so that means that I can look at this guy, Tf plus 1 minus Tf. Okay. So this guy lives in I, and this guy lives in J. Now, so f is equal to this, right? So that's clear. And in the way that I'm writing it, this is a member of Ti plus 1 minus Tj. So if f is the intersection of I and j, that means that f is in this ideal Ti plus 1 minus Tj. Okay? But by definition, f is also in the original ring. F doesn't involve any t's because it's in the original ideals. And so that means that f is also in f of x1 up to xn. So if it's here and if it's here, then that means that it's in the right-hand side. Any questions about that side? It's good? Yeah?
Why did you put t and 1 minus t third?
So your question is why I did this?
Yeah.
So why did I even do this to begin with? It's a good question. The answer is because it works. Because I mean, I agree. This is an artificial construction. It's hard to think of how whoever did this the first time how they thought of it. But the fact is that it works because I'm about to prove it to you. So this is a strange definition, but the reason it's a good definition is because the theorem is true. This definition is what allows us to intersect ideals. Yeah.
All those f's are the same.
Yeah. Yeah, all of these f's are the same f, which is what makes this confusingly easy. I don't know. I mean, it's easy to see all this notation and not see that what I'm doing is actually nothing. Did you have a question also?
I'm stuck on the second step. So how do you know that it's equal to df plus 1 minus?
So let's just do it again. So I need this inclusion, right? So let's start over, but now realize that this is really easy, and that if you're confused, it's the notation, right? It's not that I'm saying anything intelligent here. I'm saying I need to prove that this is included in this, and so I'm going to take something in I intersection j, and I call it f. Okay, and then that means that I have to show that it's in this intersection, which means that I have to show that it's here, and I have to show that it's here. Okay, now it's obvious that it's here because it's f. It comes from I intersect j, and I intersect j were ideals in the first ring that didn't involve t's. And so there's nothing to be said about why it's in this guy. Another question is, why is it in this guy? Well, if it's in this, to show that it's in this guy, I have to write it as t times something in I plus 1 minus t times something in j, and I have the freedom of choosing what I and j are. And I'm going to be so clever that I'm going to choose f for I and f for j. Okay. And then I write this equation that is absolutely, I mean, it's confusing because you don't expect to see such a simple equation in this class, right? F equals TF plus 1 minus TF, and you just cancel the TF with the minus TF, and that's it. It's all about the notation. There's really very little to say there. So is that good? I think this is good to keep in mind about Gröbner bases, that actually the proofs are all pretty simple, and it's just a matter of keeping track of the notation. Now the other side is also easy, so what am I going to do? I'm going to say, okay, we'll take something in the right-hand side. Let F be in the right-hand side. Right-hand side. This is when Laura should yell at me for writing this, and so I'll write it in Spanish. Lado derecho. Okay. We don't like acronyms so much in Spanish. So, lado derecho. Okay. So what does that mean? It means two things. First of all, F is a polynomial that doesn't involve t. Right? So F doesn't involve t, that's the first thing. And the second thing is that it's of the form t times something in I plus 1 minus t times something in j. So let me write it like that. F equals t times something in I plus 1 minus t times something in j. A is in I, and B is in j. Okay? So what kind of equation is this? This is an equation of polynomials in t plus 1 variables. Right? F is a polynomial in t plus 1 variables, sorry, in n plus 1 variables, and one of the variables is called t. So this is that one variable, and then a and b are some big polynomials involving a bunch of variables. Okay. Well, because this is a polynomial in n plus 1 variables, and one of the variables is t, that means that I can plug in. You can plug into polynomials, and you get something true. So let me plug in t equals 0 on both sides. So what do you get when you plug in t equals 0? Well, like I said, F doesn't involve t. F is a big polynomial, right? It's a polynomial in the variables x1 up to xn, and it doesn't involve t. So when you plug in t, F has no idea that that happened because F doesn't have any t's. So F stays alone. So plug in t equals 0, right? So F stays alone. What about this term? Well, t is 0, so that means that this term disappears. Right? 0 times a is 0. Now here, 1 minus t becomes 1. And what happens to b when I plug in t equals 0? Well, b is in j, right? And j, again, is an ideal in our initial polynomial ring that didn't involve t's. So that means that b doesn't have any t's either. Maybe I should write that explicitly here. A and b and f, they don't involve t. Because they're in I and j that existed before t existed. Okay. So let me just finish this equation so that it's true. So what I'm saying is that if I plug in t equals 0, b doesn't notice either. And so I get 0 plus 1b equals b. So question, Lothar?
I'm not quite sure what part A. I don't know about part A. Somehow I'm missing something.
Okay.
Why is everything in this ideal of this form?
Okay, so let's go back to part A. So why is this thing an ideal? Ti plus 1 minus tj. I'm claiming that the reason that that's true is that I can take ti plus 1 minus tj and generate it in this form. And so there's something to prove here. But it's not hard to prove, and the reason is that if I look at the ideal Ti, then you would need to prove that that guy is generated by these first guys. Okay? That's a statement that requires a proof. It's maybe a 2-line proof, but it's a proof.
Ti is an ideal
T-
because
Ti is an ideal because if you take something in Ti and you multiply it by something in the ring, then that thing is...
What if you multiply it by t? Then you get t squared I, and
Which
that's
is-
t times the nothing the original ring.
That's t times.
I mean, I doesn't involve t, so there is no t or something. That's my confusion.
I see what you mean. I think what I need to say is this, actually.
Okay, that makes more sense.
I'm a little... Let me think about this carefully, and because we don't have a lot of time, let me think about it carefully and answer it in the forum. But let me just finish the proof of the other side, which we're almost finished with, and we'll address that there. So the thing is that I plugged in t equals 0, and I got that f was equal to b. Now, I can also plug in t equals 1. So what happens when I do that? Well, again, f doesn't involve any t, so f has no idea that you plugged in anything. Now t becomes 1, a stays a, 1 minus t becomes 0, and 0 times b is 0, so what you get is f equals a. Okay? So I started with an expression of the form f equals ta plus 1 minus tb, but I showed that actually this expression cannot be anything clever. It has to be the silly expression t times f plus 1 minus t times f. That's the only way to write f. But then, you see, if f is equal to a and f is equal to b, but a is in I and b is in j, which means that f is in I and f is in j, and that means that f is in the intersection. Which is what I wanted to show. I wanted to take something in the right-hand side and prove that it's in the left-hand side. Okay. So that's the proof of part B. Let me stop there, and we'll talk about the proof of part A in the form.
The problem is I don't see how ti is an ideal of f adjoining t, and because I doesn't involve anything with t itself. And if you multiply ti as anything in ti with t, then you get t squared.